Hi, and Happy New Year. In the last video, I took care of a number of issues that have been bugging me for some time. These are things that have just piled up over time, and I wanted to get them off my plate. I also started working on the reset circuit, trying to make sure that I got a good, clean reset where I could guarantee that all of the control ROM microcode was copied from EEPROM into SRAM. While I think I made some good improvements on that, it's not working 100% yet. So that's going to be the focus today, is to get that done. Additionally, I now believe that there's quite a bit of redundancy in the clock circuit. I'm going to get into that, do some cleanup on that, and try to prepare that for what the final state is going to be. There's a lot I want to get done today. I want to get right into this.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
My wife Carrie has been working on a cookbook. Carrie's cookbook provides a unique culinary experience by seamlessly incorporating doTERRA essential oils into a diverse array of mouth-watering recipes, transforming ordinary meals into extraordinary dining adventures. The cookbook offers a treasure trove of innovative dishes that combine the health benefits and aromatic richness of essential oils with fresh, wholesome ingredients, making gourmet cooking accessible and exciting for everyone from novice home cooks to seasoned chefs. Each thoughtfully crafted recipe not only tantalizes the taste buds, but also promotes an overall well-being, harnessing the natural potency of pure essential oils such as lavender, lemon, peppermint, and basil. In Carrie's cookbook, she emphasizes the quality, flavor, and simplicity, guiding you through detailed, easy-to-follow instructions with beautiful photography and expert tips. Whether you're looking to elevate your everyday meals, explore new flavor horizons, or embrace a healthier lifestyle, Carrie's cookbook is your ultimate guide to enriching your kitchen and your life with the magic of doTERRA essential oils. If you are interested, there's a link in the description. Okay, as I had mentioned before, I've never used one of these ICs before. The monostable multivibrator has a bunch of analog circuitry around it, and I've kind of shied away from that. Probably for good reason, because I was able to trace down a few of my issues to that particular IC. Now, I suspect that a lot of it is going to be related to the fact that I am on Breadboard, and that may go away in PCB form, and it could be that I just have no clue what I'm doing, and I'm going to have problems in the PCB as well. First, let me refresh your memory on what the problem is. These LEDs here are supposed to operate sequentially, where the first LED is while the copying is taking place here on the control ROM midplane. The second LED is while it's clocking to clear out the CPU registers, and then the final LED is supposed to be in running mode. On reset, this transitions to copying very quickly when the clock is running. When the clock is not running, that does not take place. That actually is operating exactly the way I'm expecting it to. And what I've traced it down to is, let me turn the clock back on, and I'm going to go into pin 4 of this monostable multivibrator. This is the inverted output Q, so this should be a normally high signal, and then go low with every trigger that takes place. Watch the scope. As I reset, I am actually getting, and I'm hoping this shows up on camera, I'm actually getting a trigger with every single clock cycle that takes place here. And then this last one here is the actual pulse that indicates that it's done copying. Well, that's the incorrect behavior. If I was to turn the clock down here off and leave it in manual step mode, that again is operating properly. And there I get the proper signal. I can step 7 times, and then it advances on to the running mode. So the challenge I'm having is that when this clock is running, something is sympathetically causing this to trigger, causing this LED to advance. Well, in doing some digging, I found this document. And it was an interesting read, and it's specifically about how to design with the LS123. Let me share with you the highlights. See what I did there? I highlighted it. Anyway, smartass aside. So in here it talks about making sure that the Q output traces stay away from the clear lead, which is one of the inputs into the monostable multivibrator. And then if it happens I get constantly high outputs with 50 nanosecond low spikes determined at the frequency set by the resistor and capacitor external to the IC. It also offers a solution if a sufficient trace isolation cannot be obtained. A 50 picofarad capacitor between the C lead to ground usually eliminates the problem. I'm going to grab one of those and see if that doesn't solve this problem, but I don't believe it will. Okay, so here I have a 47 picofarad capacitor. Hopefully that will be good enough. And these are ceramic capacitors. And my C lead is on pin 14. So if I bypass pin 14 to ground, now let's give that a shot and see what that does for us. Power it back up, turn the clock on, pin 4, reset, and that is still showing a change with every single clock cycle. So that capacitor did nothing for me. So I removed that capacitor. The next thing that got me thinking was this line right here. Now this paragraph says that the B input is designed to handle pulses with a slow transition. It's tied to a Schmidt trigger, which in and of itself doesn't mean that it should create this problem. However, that does imply to me that it is designed differently than the other signal. And if I go back to the function table of the 74LS123, I'm using B. When B goes high, I get my pulse. Clear, if I do a transition from low to high, I get the same pulse. So I started thinking, what if I was to swap my B, which is the input that I'm using, with clear, which is tied high? Both clear and B in my two scenarios are tied high. How would that behave? Alright, so let's give that a try. And then turn the clock on. And that is no longer triggering with every clock cycle. That is now holding through the entire copy, then switches to clocking and then goes to run mode. That is the behavior I've been looking for. Now, if I power up while holding the button which puts the clock in run mode, that's still holding there. I am getting clocks, and that also works. Okay, while I don't like the idea of arguing with success, I really can't explain what the difference is here and why this is working now versus why it wasn't working before. If you have a better understanding of what's going on here, please help me out in the comments. I would appreciate the assist on this because I am well outside of my comfort zone here. Thank you. But that doesn't work. That's the next issue that I think I need to solve. These bottom two breadboards here are my clock circuit. Now, there's some redundancy that exists down here that I need to be able to remove, but I'm going to spend a minute and orient what's going on here. This is my single step switch. This is my potentiometer for adjusting the clock speed. And then I've got what I am calling a high-speed system clock up here. I have a total of 3555 timers on here. This single one is used to debounce the single step switch. This bottom 555 in the 556 package is used as my adjustable clock speed. And then this upper one here is fixed and it is a high-speed clock. Ultimately, I want to replace that with a crystal. The 74LS74 is used to divide down both the adjustable clock and the high-speed clock to make sure that I've got an exact 50% duty cycle. The 74LS151 is used to select between which of these three clocks are presented out onto the clock signal. I only need to manage now between my single step, my variable, and the high-speed clock, and that will be done using a 3-condition latch now. I have two set reset latches on this NAND gate here. One of them here on the right side is used to indicate whether I'm resetting or not resetting. I've got that signal now available to me up here, so this is redundant. And this set reset latch is used to indicate whether I am in running mode or single step mode. This counter was intended to do the same thing that this counter up here does. And since that functionality now exists in my reset circuit, this can go away along with its dip package here. Finally, the line driver here is used to drive the LEDs. So there are a few redundant pieces here that now need to be removed, one of which is the counter here, and then this set reset latch can go away, meaning I believe that once I get those taken care of, even though I've only got 2 options left here for the multiplexer, I believe I'm going to end up with a cleaner reset on cold restart. Let me start pulling components. Reset is no longer used as an input here. And now I have several wires that are no longer used. The dip switches can be eliminated. Along with all the dead-ended hookup wires. The 74LS183 can go away. This unused set reset latch can now go away. This now brings up the first 2 signals which really now need to be reset. An input into the line driver for the LED, now always low. An input into the multiplexer here for select C, again, always low. And then this extra reset LED here can go away. I now believe I'm in a pretty good position where I can actually test a cold reset. And what I had figured out was that this set reset latch wasn't being driven correctly, which was giving an odd output to the C selector for the 151 multiplexer, which would then give me odd signals for reset and what was going on with the clock. I believe that's actually what was driving the instability over here. Let's test that. One good reset a pattern does not make. That's 4 good resets, and I am pleased with that. Now, I'm not going to say that that's perfect, but that's certainly much better than I have had it. Now I need to start looking at how I'm going to build all of this back up again. Okay, now that I'm enjoying something that resembles stability, what I want to do is I want to clean up the schematic associated with this change with the multivibrator. I also want to clean up the emulator to make sure that I reflect this as well, and check that the emulator is actually still working. Let's start with the schematic. This is a rather simple change. It's just a matter of swapping pins 2 and 3 on this gate. Still clean. This is the same thing. Swap pins 2 and 3. Now that it compiles successfully, let me clean up my commented code, and then I will run a test. Nice. Okay, let's get into an updated version of the clock module. What is this going to be? Iteration 6, 5 maybe? I don't even know. But I want to get into a block diagram of exactly what I want this to look like now. I'm hoping this will be the final version. This one that I'm using now has served me well, but I do believe that I'm going to be able to improve the performance of the clock. So I want to kind of prepare for that and take that into account. Here is what I have today, and some of this is going to get reused, so I do want to move that out of the way, and I will then start with what is in effect a blank sheet here. Like I did with the reset module, I want to design this kind of in a top-down approach. Okay, I have a few design considerations that I want to take into account as I am going through this. The first of which is going to be that I actually want 3 different clocks that I can utilize in the CPU. The first is going to be a dividable crystal oscillator. The second is an adjustable clock. Now this is the one that's going to be adjusted based on the potentiometer. The final clock would be a single step clock. A feature that's going to be very nice to have, I'd almost call it a requirement, is to have a break signal coming from the control logic midplane. Now this signal will put the clock into single step mode, stopping the clock so that I can do debugging at a particular point in software. I also want the ability to manually put the CPU into single step mode, so a push button is going to be there as well. Next on reset, I want the adjustable clock to be selected automatically. Now, I may get some pushback on this choice rather than putting the clock into single step mode on reset. But my thinking is that I can actually use the break signal as the first instruction if I need to manually debug anything that's going through the system. I find that I will more than likely be debugging things deeper into logic than right at the outset of the start of execution. I may be wrong on this, but this is the decision that I'm going to make and the way I'm going to architect this. I find it, as long as I've got my break signal working properly, I should be able to stop right after the first instruction, which will be the break. Now, the last thing to consider here is what type of clock transition synchronization do I need? And I'm not exactly sure how to answer that question yet. My concern is that if I transition from the crystal oscillator to the adjustable clock or vice versa, I may end up with a very narrow signal which may not be able to be handled properly, and I may introduce bugs in that transition. So there is a block that's going to be placed into the block level design, which is going to handle that transition synchronization. Again, I'm not exactly sure what that's going to look like yet, and I am likely to fumble over this for a little bit. Okay, so for a basic block diagram, I'm going to start with the dividable crystal oscillator. To that, I will add the adjustable oscillator. And finally, I need a single step oscillator. Each one of those are going to feed into a subcircuit where I can determine which is the actual active clock. And finally, I've got a subcircuit that's going to handle the transitions from one clock to another. Okay, let's start with a single step oscillator. That's actually a trivial copy of that subcircuit. And I do need to change the output type. Likewise, the adjustable clock is just this subcircuit. For the divided crystal oscillator, I'm going to steal the counter IC from the reset circuit. It's almost exactly what I need. The only material change here is to take the borrow out and use that to trigger the load. Finally, I'm going to go get the crystal oscillator from the control ROM control module. It's got the footprint I want to use, so that'll save me some time down the road. Finally, I have just a few things to clean up. State is another subcircuit I can lift off the reset module. After copying and pasting the entire subcircuit, it's just a matter of going through and removing the things that I no longer need. I will label the outputs. And then I need a push button for each of the oscillator, adjustable clock, and single step clock. Okay, the rest of this I left off to the side. I am no longer going to need and or want to use, so we'll remove that. Finally, let's talk about the interface points. I'm going to go with a 16-pin header. Let's put ground and then VCC on the schematic. I need two clock outputs. One is the system clock or the high-speed clock. It's going to be the highest clock I have available. The second is going to be the CPU clock. Now that's the one that's being manipulated by the clock circuit and all the different push buttons. Finally, my two inputs are the reset signal and the break signal. I may come back to this and revamp this connector to have two just for physical stability of the PCB. Okay, let's get into some more of the details of the oscillator. There's one output I actually need to add to this, and this oscillator itself is going to drive the system clock. So I want to put a system clock output here and connect that up to the oscillator output. The whole purpose here is to take the highest clock speed possible and use that to drive the control ROM copy. The adjustable clock only needs to have a couple of cosmetic things taken care of. Same with the single step oscillator, only a couple of cosmetic things. The next subcircuit I want to take a look at is the state. Now this is an incomplete circuit at this point, and it still has a number of things that are left over from the reset module and how that was actually decorated in the emulator. First thing I'm going to do is center this up a little bit better, and I'm going to remove these references that were used in the emulator. Next up, I want to take care of these switches. These are going to be active low signals, so when I push the button down, I should get a low signal, which means I will need pull-up resistors. 10K resistors, please. Now, I said that on reset, I want the adjustable clock to be automatically selected. Reset is an active low signal, the push button is an active low signal. If either of those go low, I want the resulting input into the NAND gate to be low. So both of those signals have their default state to be high. That's an AND gate. The next signal to take a look at is the break signal. Now this one is an active high signal, and the push button right now is an active low signal. Now I do have the ability to change that, and I actually have an extra NOR gate that's available. So if I was to change the switch 9 push button to be an active high signal, and then if the signal break coming in was an active high signal, and I use that remaining NOR gate for shaping that signal, if either of those two went high, then the output would go low, which would be the correct signal I want to trigger the single step mode. Let me name these switches. Okay, let me pull these new connections into the subcircuit. Now for the clock transition subcircuit. This is going to be responsible for the transition between the different clocks to make sure that that happens cleanly. So for inputs, I'm going to need all three clock signals and all three clock selections. The single output will be the CPU clock. Let me import those into the root. All right, I'm going to use these unused AND gates. So for each of these clocks, I only want them to be passed on when that particular clock has been selected. Now the two oscillators are going to end up being different than the single step clock. So for the two oscillators, I want to be able to combine those two signals together. And then I want to feed the output of that into the clock of a D-type latch. This D-type latch is really dividing the clocks by 2, and this should smooth out any issues I have with transitions, at least between the oscillator and the adjustable clock. Now the question is, on reset, do I want this clock to be high or do I want this clock to be low? I believe on reset I'm going to put the clock high. That way I end up with a half a cycle to try to settle things down before I'm executing code. I think that's going to work. Now really what's left is to combine the two clock signals and route it to the output CPU clock. Okay, let's see if I can't put some polish on this now. The first is a naming convention problem. And if I look at the reset circuit, the input is called a HS clock for high-speed clock. But in the output here, but on the clock module, I called it the system clock, and that is an incorrect name. So I need to clean that up. Next I have the CPU underscore clock, but the input into the reset module is CPU clock without the underscore. So I'm going to make the clock module match. Next I've changed my mind here on this transition circuit, and I want the clock to be held high while I am in copy hold, not just the reset itself. I definitely need the clock cycles after the copy hold in order to clock the instruction and fetch registers to be empty. So I'm going to change this to be copy hold. And I actually need to bring that signal in. And so I will do that here. Okay, now to arrange this a little bit better so I have a little bit more room. And then I will start hooking everything up. Okay, I have some of the unused gates down here that I added directly, but I don't have everything represented. For example, I've got 4 NOR gates here, but I don't have its package and power. I have 6 NAND gates, but there are 2 that are missing, and I need to get those taken care of. Now I'm going to redo all of the annotations, and that should clean everything up nicely. Next up, I want to add 3 LEDs to indicate which of the 3 states I'm in. Now, as a design consideration, I don't like directly hooking the LEDs up to the signals. I'd rather run them through some sort of a gate to act as a buffer to isolate the signal itself from the draw or drain of the LED. I have 4 unused gates that are on this, and I'm going to select 3 of them to drive the different LEDs. These are going to be used as buffers. Now this also has me thinking, I think I want to add in a 4th LED for the CPU clock. Let me do that. Okay, 1 unused gate. And finally power, ground, and decoupling. Okay, let me place a couple of power flags, and then I will run the electrical rules check and see what I end up with here. Alright, try that again. I've got a modification to an object. Aha! Very good. The next order of business is going to be to update the clock module in the emulator. Okay, I am relatively certain I have this working properly now. Now, I'm going to fast forward through this during the copy, but just before it's done copying, I'm going to set the speed of the video back to normal speed. So while debugging the emulator, I found all kinds of issues. A good number of them were just stupid mistakes that I had made, but there are some errors in the schematic. I'll get to those here in just a second as well. Now I'll set the oscillator so that when it's done copying all of the control ROM logic, it goes into very high speed mode. Again, that will be in real time. Also of note is single step is working, and I can bounce back and forth between the high speed oscillator, which is currently divided by 1, the adjustable clock, which is divided by that speed potentiometer, which is a sliding potentiometer, and then I can single step. Break also works. It puts the clock in single step mode. Before I made this change, it used to be that the copy took about 20 minutes. Now it takes roughly 15 minutes for the control ROM to copy in the emulator, so I did get a bit of a performance improvement with this as well, at least for the emulator. And I will have this sped up so you don't have to sit with me for 15 minutes. And back in real time here, that moves pretty quick. All right, let's get into the schematic corrections. Okay, there are a number of issues on this page, but I don't want to start here. I want to actually get into the details and let those details bubble up to the top. On this sheet, this is probably one of the bigger changes. I had to add an AND gate in here so that I could shape this signal here properly. The problem was that I was able to latch this when that clock was in a high state. Well, a high state or a high or a low is always going to result in a high state. I couldn't single step my way through anything after I had paused. So I decided to shape this signal. I thought I could OR a couple of things together, and then so if the oscillator select or the adjust select were high, then I would be okay to go into this AND gate and pick up the other signal, the output signal off this latch. Well, this unfortunately sets up a race condition, so I couldn't use that. Ultimately, what I decided is I was able to use the inversion of the step select ANDed with this Q output, and that would shape that signal properly, and I wouldn't get an errant bounce in there or an extra clock cycle if I was transitioning to the single step clock. So this AND gate needs to get placed in here. Let's go to KiCad. Okay, for reasons that I hope are going to make sense here in just a second, I'm going to start by placing that IC on the main sheet and then drag the gate that I need over to that transition page. Okay, off of here, I now need to get an inverted step select. Okay. The next thing to take a look at is the latch. I once again got the set and reset signals backwards, so I need to clean that up. On this sheet, the set reset latch here uses gate 3 for set and gate 4 for reset. When I wire those up on the breadboard, typically I'd have those backwards, so I want to swap those so that gate 4 is up here and gate 3 is down here. So my last task here is going to be related to cleanup here. Now I inadvertently put NAND gates in here to drive the LEDs and didn't take the proper wiring into account. But I now have 3 unused AND gates, so I'm going to swap those out, keep the wiring the same, just use an AND gate, not an AND gate, and reposition so that I can squeeze in the extra capacitor and IC for power and ground. All right, let's wrap up with an electrical rules check. Not sure how I managed to pull that one off. That's probably because I moved it instead of copied it. Very nice. Well, if you were paying close attention, you realize that I have taken the output of this high-speed oscillator, the one I'm intending to be 10 megahertz, and I have connected it directly up to the high-speed clock signal. I'm not dividing that in any way. Now that same signal is used on the control logic midplane to control the copy of all of the control logic from EEPROM to SRAM. Is 10 megahertz too fast? Well, let's test it and find out. So here's my 10 megahertz crystal oscillator. I'll drop that in here for now. I'm going to hook up power and ground. And then up here is my output. Now I'm going to take the system clock and the high-speed clock connection over here to the control logic midplane and hook them up to the output of this oscillator. Place your bets. Well, that looks very promising in that it's actually presenting the correct output here. If I reset, that is a very quick copy. Yeah, it happens that quick. So let's spot check some of these other values here. Now I went through several instructions here comparing the actual LEDs that were lit up against the control ROM code itself to make sure that each instruction was actually accurately represented. I did a handful of them, maybe 5 or 6 instructions, and they all turned out good. I think this is working. I think 10 megahertz is a good reset. Okay, so here's the 3 breadboards that I'm going to use for the clock circuit. Now I have gone ahead and soldered the capacitors on underneath the IC so they sit in the gully. And then for the 555s, I've just got them sitting off to the side. So that's the decoupling. Decoupling is in place for the power rails. Let's get power and ground. Now for the unused gates. That's wrong. This is rotated 90 degrees. LEDs. Dip switches. Counter inputs. Found another issue. Adjustable oscillator. Yep, I messed this one up too. Single step oscillator. Set reset latches. These are wrong. Push buttons. For the sake of being able to hook up these last 2 gates fully, I am going to need to have this input-output interface point defined on the breadboard. To that end, I've laid this out. Now my connection point is going to be the middle row down here, so I will be able to take off from the top and bottom. So there are power and ground that needs to be integrated in here before I can actually take the signals and move them off to the gates here and here. Now those last gates. The last thing to look at is this clock selection logic. Let's start with the latch. The last thing to hook up are driving the LEDs down here. Now I'm going to reorganize these gates on the breadboard to be what makes the most sense for the breadboard. I'm not going to update the schematic. It really doesn't matter which one's hooked up to which. Single step, final clock, adjustable clock select, oscillator select. Let's give this a test. This is the old clock module, and what I want to do is remove this, put this in its place, and then make all the appropriate connections here for the copy, hold, reset, and then take the signals off. So I'm going to give this a shot. I'm going to spend no more than 5 minutes troubleshooting, and then if this works, great, and if not, then we'll go ahead and kick it into the next video. So I am on the single step clock selected. Yep, something is not right here. Okay, so after some digging and some probing, I have figured out that this purple hookup wire is actually going to the wrong gate. It's supposed to be all the way over here to this gate. Let me get that reworked. Now at this point, this may work, this may not work, but there's also another thing that I want to call out here before I get into actually testing that. Now I know I just made this change, so it may change the behavior here. I doubt it will. Okay, so power. And this is my reset signal. And after reset is complete, that signal is supposed to be high, but that's a big mess. Now, I believe it to be related to this 10 megahertz clock, but it may be slower than that. I'm not exactly sure. But if I come up here and I tie into the same ground up here, my ground is a mess too. This is the ground from here to here, and I know I've got an extended long lead, so part of this could be in measurement. But I don't think the ground is supposed to be that kind of a mess. If I take the crystal oscillator out, that smooths things out right away. Now I know that that crystal and that frequency on breadboards, and in particular the rise time associated with that, can, and will make a mess of things on the breadboard. One of the things I'm wondering is if I don't put the crystal on this wire power and ground back to the actual point up here, so I've got more of a star type distribution, and would that improve things on the breadboard? I'm not sure, and this is where I'm going to leave it because I'm going to have to do some thinking on this, and I know the video is getting a little bit long, so I've got to think more on the oscillator and the responses I'm getting out of that and how I can isolate that a little bit better on the breadboard so I can continue this build. That is going to force the order of the clock circuit far sooner than I had intended, unless I can get something that's going to be relatively stable here. So the crystal oscillator is creating a bit of a mess on my breadboards. Now, how much of this is breadboard related and how much of this is bypass or decoupling related, I'm not really sure at this point. I've got some thinking, some research, and the like to do. Now, I know that Dave Jones has done a video on bypass capacitors and what the favorable responses are and potentially negative responses are related to adding bypass capacitors to your circuit. I'm going to spend some time and watch that a couple of half dozen times, see if I can understand exactly what it is that I'm looking at. I've also got some research to do on other things related to breadboards. I know that there's a lot of impedance issues that develop in those as well. So I want to try to understand that so that on the next video I can get in and at least, I'm not going to solve the problem, but I want to mitigate it. I still have an issue with the 3-state latch that I've got on the clock module. I wired something silly, so I just need to get in and get that solved as well. We'll start with that in the next video, and then if all goes well, we'll get this translated into a PCB. Like I said, this is going to need to be ordered sooner rather than later. We'll see you soon.